Welcome aboard. I'm Jenny Lee from the University of Alberta student team, ARVP, presenting our submission for the 2021 RoboSub competition. I am a fourth-year petroleum engineering student, but more importantly, I am the project lead for this year. This past year, we have focused on developing our newest underwater autonomous vehicle, Arctos. And now we would like to highlight our progress and accomplishments.
Hello, my name is Nigel Whithouse, and I graduated with a master's degree in computer engineering.
Hello, my name is Nina Yang, and I am a fourth-year mechanical engineering co-op student. And we are the admin co-leads for ARVP.
Hi, my name is Justin, and I'm a fourth-year computing science student and software team lead for ARVP.
Hello, I'm Kirill Makachev. I'm back in school for a master's in electrical engineering, and I'm the electrical lead for ARVP.
Hello, I'm Drew Del Ciopo.
And I am Jared Schroeder. We're both in our fourth year of mechanical engineering.
We're the mechanical co-leads for ARVP.
Throughout the past year, we have designed, modeled, and manufactured Arctos, our competition robot for RoboSub 2021.
Throughout the past year, we have planned, designed, and created to ensure competition readiness of our new robot, Arctos. Last year, we unveiled Arctos, ARVP's newest creation in a long lineage of autonomous vehicles. The hull is the backbone of our AUV. In order to achieve an efficient hull design, several criteria must be met. The hull must be structurally sound, waterproof to safeguard electronic components, and it must contain enough space to support all critical subsystems, including our torpedo launcher, robotic arm, electronics trays, cameras, DVL, propellers, and more. A huge design consideration is accessibility, the ability of a team member to manipulate, add, or remove components from within the hull. This hull design is critical for team success. It must support all other components, and if minor defects emerge, such as failed seals or incorrect dimensions, it can spell doom for Arctos before it even hits the water.
Unlike previous designs in ARVP's repertoire, Arctos is the first to feature a square hull instead of a cylindrical one, increasing the usable space to volume ratio from 0.5 to 0.7. This means we can fit more components inside the hull.
Hi, I'm Abdallah. The square hull creates many engineering challenges related to waterproofing and structural integrity due to stress concentrations along the hull's edges and faces. The team paid particular attention to clasping mechanisms, seals, O-rings, wall thickness, and manufacturing methods to ensure leak protection and reduce the probability of various failure modes. The T6061 1/4 inch thick aluminum hull makes Arctos lightweight and strong. It is hard ionized for increases to durability and longevity. The hull measures 14.75 by 7.5 by 18.5 inches. Overall, the entire robot is 24 by 24 by 28 inches and weighs 80 pounds, just under the design requirements for the competition.
The hull is the basis for all other subsystem designs. 8 propellers are connected externally that not only control the thrust, but also the roll, pitch, and yaw of our robot, giving us 6 degrees of freedom. The square hull and skeletal frame promotes flexibility in the attachment of external mechanical and electrical subsystems, such as the 3-axis articulated claw, torpedo launching mechanism, and cameras. This design is advantageous because we have complete control in customizing the position of all these external subsystems, that we can easily modify our design to best satisfy competition objectives and our strategy best. Previous AUVs designed by the team were unable to satisfy certain task requirements due to design limitations. For example, Ori was unable to fully satisfy the collecting bins task because it lacked an articulating claw. Its predecessor to that, Aqua Ursa, was large and cumbersome and had difficulty controlling its 3 axes of rotation, particularly pitch.
Both of these shortcomings were related to hull design. We have learned from our mistakes and implemented the solutions into our current design, making the hull sleek and the design modular, has solved previously mentioned issues faced by other ARVP robots. Based on our current mathematical models, simulations of Arctos, and our achievements in previous RoboSub competitions, we can estimate our performance in the 2021 RoboSub competition as if it was in person. For the following analysis, we are referencing the point breakdown model from the 2019 RoboSub competition. For our hypothetical competition run, we assume that we take the G-Man path.
Based upon weight and size restrictions, Arctos weighs 80 pounds. Thus, we will receive a 7.6 point bonus. We begin the competition either facing perpendicular to or away from the gate, decided by a coin flip. Arctos can handle either scenario and rotate to find the gate with 100% confidence. We should be easily able to pick the G-Man side of the gate. Passing through has been no difficulty of ours, as can be seen in this 2017 footage, though there we did not perform any rolls. From our simulations, we should be capable of performing 8 90-degree rolls for maximum style points. However, until we physically test a robot, there is uncertainty. Thus, we give this 75% confidence. Our computer vision algorithms have improved from past years, and we should be able to follow both segments fully with 100% confidence. We assess a 95% confidence of correctly ramming the badge buoy, thus completing the task.
This task has a lot of complexity. As our claw is a new subassembly, we may have difficulty lifting the covers off the bins. Thus, we will give this a confidence of 60%. From past years, we have not attempted the dropper challenge. We have a newly designed, streamlined torpedo dropper, which should be extremely accurate, and expect a 70% confidence of dropping into the G-Man barrel. We've been perfecting our torpedo technology for years, and have an improved system this year by including a 3D stereo camera. There is a lot of variability and uncertainty related to this task. In 2019, though, we narrowly missed by an inch. With the added stereo camera, we can more precisely determine our distance to the target and the exact location of the torpedo target. We assess an 85% confidence for this task. We have learned from experience that navigating to and surfacing inside the octagon is of no difficulty. However, combining both computer vision and claw manipulation remains a hurdle. Overall, we should reach the surface with 100% accuracy. Surface with the bottle at 60% accuracy, and move the bottle to the G-Man X table with 60% accuracy. From our simulations, we would expect to take up to 14 of the available 15 minutes. Hypothetical assessment of the criteria mentioned, we would expect to earn 6,507.6 points.
Hi, my name is Rachel. Arctos has been in development for 2.5 years. We've been fortunate enough to rely upon the experiences of previous members and the extensive knowledge they've supplied from our team's 25-year-long operation. With the accomplishments and shortcomings of our previous robot Ori, we knew how to improve upon its design when creating Arctos for this year's competition. All of our design components go through a similar development cycle. We begin by understanding the goals and requirements of the system. For subassemblies such as the hull, we begin by asking basic questions. How do we make it structurally sound while respecting the weight limit? How do we make it waterproof and prevent corrosion? How do we make internal systems more accessible? What hull shape best lends itself to our goals? From these questions, we can assess the validity of different designs using simple tools such as weighted decision matrices and risk assessment matrices.
We can further our inquiry by using more technical design platforms. Considering the hull, we can assemble our ideas in SOLIDWORKS, test out stress calculations in ANSYS, and gauge the robot's performance in Gazebo. Once our robot is fully assembled, we take it to the local pool to officially test our work. It is a team effort to collect data and gauge the robot's performance. From the results of these tests, we take it back to our original questions to further improve our designs. This is a scientific method in a nutshell.
This past year has been challenging for us due to the COVID-19 pandemic, as we're sure it has been for many teams engaged in RoboSub. Campus, work sites, and pools were all closed through the entirety of the pandemic, making a lot of our initial desires and wishes go unrealized, with many of us having to work in our homes. Despite all these setbacks and obstacles, ARVP has continued to thrive and engage its members meaningfully. ARVP has been quintessential to our members' university experience, like mine. The occasional game of Scribble.io, Unrailed, and Minecraft were also beneficial, not to mention the ARVP Vault server for working on solid models remotely. Like this one.
We have quickly and efficiently adopted our workflow and goals in the face of adversity by moving team functions online. Our team rely upon digital mediums for communication and coordinated remote work. Remote communication promotes greater flexibility in relation to work sessions and meeting time and has thus been extremely beneficial. Members could work on their tasks at their leisure in response to flexible deadline. In our current phase, Arctos' major components are being assembled and tested individually. As more vaccines become available, COVID-19 cases will continue to decline. Our team has been working super hard with our supervisor, Dr. Lipset, to create a plan for return to in-person work on campus. We hope to return to regular team operation and to fully assemble Arctos and test its functionality by the end of the summer. That means we'll have an entire year to improve Arctos and be ready for RoboSub 2022. See you there!